some basic definitions about integral equations, and we reviewed the definition of Fredholm integral equation, Volterra integral equation, and also integral differential equations. Up to now, we know that when we talk about Fredholm integral equation, actually we work on the integral equation that in the integral part we have constants in the lower and upper bound of the integration. For example, the integral of some expressions from A to B. And when we talk about Volterra integral equation, we actually discuss about the integral equation that their integral part is something like this. This is just an example, and it can have different forms. For example, you can have here variable and here a fixed number, or both parts, both bounds, lower and upper bounds, can be variable as well. So we want to continue our discussion and be familiar with the other types of integral equation. Here we see the different type of singular integral equations. Let's start with the definition and see the actually difference between first kind and second kind singular integral equation. If you remember in the previous discussions, when we talked about second kind and first kind, we refer to the function f being 0 or non-zero. When actually have f equals 0, we have homogeneous integral equations, and when the function f is non-zero, we have non-homogeneous or inhomogeneous integral equation. And for being second kind, we should have u, the unknown function, outside the integral and also inside the integral sign. But here, when we talk about first kind singular integral equation and second kind singularity, it's a little different. Let's see here the integral equation of the first kind. You see here that we don't have the function u, which is our unknown function, outside the integral part. We just have it in the integral sign. So this equation in the different, actually different categories we defined, take the type of first kind integral equation because we have it in the integral sign only. And also the integral equation of the second kind, because we have the unknown function outside the integral also. We call these two integral equations singular if we have one of these situations. The first one is that the lower limit, for example, here, alpha, or the upper limit, beta, or both of these limits of integration are infinite. It means that we have something like this. Here we have negative infinity to A or to B, for example, it's more suitable to use, or we have A to positive infinity, or we have the integral from negative infinity to positive infinity. For all these three situations, we call these two integral equations as singular integral equation. So one type of singularity refers to these situations that one or both limits of integrations are infinite. For example, here you can see different singular integral equation. For example, here, can you tell me why we have singular integral equation? Why this integral equation is singular? Can you tell me?
Yes, Doctor.
What's the reason, Mr. Mohammed?
Doctor, limit under limit 0 and upper limit infinity.
Exactly. Since we have this upper limit infinity, so we have a singular integral equation. And for the next example also, we have the lower bound as negative infinity, and it makes this integral equation as a singular integral equation. And also for the third case, we have both a lower and upper bound of integration as negative infinity and positive infinity. So one kind of singular equations can be recognized by the limit of integration, and another kind is a little different. I stop because it takes time to the next slide be appeared for me. Right now I have it. Okay, let me continue. Okay, and the other class of singular integral equation includes the actually integral equations that the kernel, the function k of x and t takes the value infinity for some actually values of t. For example, let me read the explanation here. In this case, the kernel k of xt becomes infinite at one or more points in the domain of integration. So by this way, we can recognize that if an integral equation is singular or not. For example, you can see some different examples here. In this case, if you consider k, as you can see, then it's completely clear that when t approaches x, then the value of the kernel will be infinity. And also here, we have the kernel 1 over x minus t to the power alpha for all alpha between 0 and 1. So once again, you can see that when the value of t approaches x, then this kernel takes infinity value. In the case equation number 24 and equation number 25, actually we have first kind singular integral equation because we don't have the function u outside the integral sign. But in the last example, equation number 26, you can see that the unknown function u can be seen outside and inside the integral sign. And also you can see that here the kernel once again takes the value infinity when t approaches x. So this Mr. Hadi, do you have any question? No? No question?
Sorry from the internet in the Iraq, but now
Huh?
no problem.
Okay, okay.
Okay,
So-
no question.
So this is again a singular integral equation. For the case equation number 24 and 25, they are called actually a special integral equation. For example, equation number 24 is called Abel's integral equation. If you compare this integral equation and the next one, you can see that this one is a special case of the second one, because when you consider alpha equals 1/2, this kernel will be 1/√x minus t. So the second kernel actually gives the first kernel when we put alpha equals 1/2. So equations with this kernel, which are first kind integral equations, are called Abel's integral equation. And the second one here, this one, and all equations similar to this are called generalized Abel's integral equation. But as I said, the third equation is a little different because we have the unknown function u outside the integral sign also. We call these kind of equations as weakly singular second kind ultra integral equations. So these three equations are very important, and each of them has a special name that you can recognize these kind of equations by their properties. Let's go to the definition of Wolff-Raffer-Hertzsprung integral equations. As it is clear from the name, when you are talking about Wolff-Raffer-Hertzsprung integral equations, it means that you have both part of a Wolff-Rayet integral and also Hertzsprung integral in one equation. For example, you can see a general form of linear Wolff-Raffer-Hertzsprung integral equation. As you can see here, in the first integral, the upper bound of the integration is a variable. So this makes the Wolff-Rayet part of this integral equation. And also in the second integral, you have both lower and upper bounds of integration as constant or fixed numbers, and this part makes the Hertzsprung part of this integral equation. So since we have both Hertzsprung and Wolff-Rayet parts, we call this kind of equations as Hertzsprung-Wolff-Rayet or Wolff-Raffer-Hertzsprung integral equations. You can see in different books, both names. In some books you see Fredholm-Volterra integral equations, and in some others you can see Volterra-Fredholm. There is no difference. It means just that you have both Volterra and integral type actually parts in a equation. The functions k1 and k2 are kernels of the equation. For example, here you have the equation number 28, and you can see that this is the Volterra part, and this is the Fredholm part of the equation, because both lower and upper bounds of integration are constants, but here you have variable upper bound. Can you tell me if this is second kind or first kind integral equation?
First integral equation.
First? Why first?
Because there is no equation f of x equal to e to x or x square.
No. When you say first kind or second kind, it refers to the presence of the unknown function outside the integral sign or only inside. When you say second kind, it means that the unknown function, which is u here, appears in outside and also inside the integral sign. Since you have this function in these two situations, so this is second kind, because the unknown function u is seen outside the integral and also inside the integral sign. This is second kind. And about being homogeneous or non-homogeneous, can you tell me if it is homogeneous or non-homogeneous?
It's not equal to 0.
This part, which is equivalent to the function f, is not equal to 0, so this is inhomogeneous integral equation. And for the second one, equation number 29, once again we have Volterra part, Fredholm part. The unknown function is also outside the integral sign, so this is second kind. Second kind, and also this is an inhomogeneous integral equation because we have f of x, this function f of x is not 0. So this is, if I want to describe this integral equation, I can say that we have a second kind inhomogeneous Volterra-Fredholm integral equation. Okay, the next topic is about Volterra-Fredholm integral differential equation. If you remember, integral differential equations refer to a class of integral equation that both derivative and integral of the unknown function appear in the equation. For example, here you have the derivative of the unknown function u of order n, and also you have the integral of the unknown function. And once again, since you have Voltro part. And Fredholm part, you call this equation as Voltro-Fredholm integral differential equations. And this is a general, actually a standard form of the Voltro-Fredholm integral equation. And as you can see, this is a linear equation where K1 and K2 are the kernels of the equation. For example, here you can see an example of the Voltro-Fredholm integral differential equation. And as you know, since the order of derivative is 1, we need one initial condition. So we have Voltro-Fredholm integral differential equation. In the second example, we have the second order derivative of the unknown function u, the Voltro part, Fredholm part, and two initial conditions according to the order of derivative, which makes this integral equation, integral differential equation, actually complete. Notice that the unknown function u of x appears inside the Voltro and Fredholm integrals and outside both integrals. Here, we want to classify this integral equation. We have some different examples that you can actually answer me about the different properties, of these integral equations and which classification they actually belong. For example, for this case, equation number 33, can you tell me if it is Voltro type or Fredholm type, or the mixture of them?
It's Volterra.
Voltro, because this upper
0 to
bound,
x.
yeah, exactly. This upper bound is variable. Can you tell me it is linear or non-linear? Yeah, exactly,
Linear.
because you don't have non-linear
Yes.
function in terms of u. Okay, so it's linear. It's homogeneous or inhomogeneous?
Non-homogeneous.
Exactly, non-homogeneous or inhomogeneous. So this is a second kind, because u of x is outside the integral. This is a second kind Voltro integral equation, and it is a non-homogeneous equation. Okay, let's go to the next example here. Is it Voltro or Fredholm? Fredholm, exactly. Because both upper and lower bounds are constants. Is it linear or non-linear?
Non-linear.
Exactly, it's non-linear because we have power 2 of the unknown function here, and it makes it non-linear. Is it second kind or first kind?
Second kind.
Second kind, exactly, because u of x is also outside of the integral sign, so it is second kind. And about being homogeneous or non-homogeneous?
Non-homogeneous.
Non-homogeneous, because we have the function f non-zero. The next equation Is it,
Volta.
yeah, exactly, Volta. Is it integral equation or integral differential equation?
Yes, into differential equation.
Integral differential equation, because we have the derivative of the function also here. And is it linear or non-linear?
Doctor, non-linear.
Why non-linear?
X power 3.
No,
No.
let me explain it. You just consider to check the linearity or non-linearity. You have to just consider the function in terms of u. If
U
the
of t.
function u appears in nonlinear form, you call this nonlinear. But if the functions in terms of u appears linearity, you call them linear. Since the function u appears in a linear form, you call this linear integral equation, okay? You don't have to pay
Okay,
attention
doctor, okay.
to the other variables. You just have to consider the functions in terms of u. For example, if you had here u squared, then you had nonlinear. But since you don't have this case or another cases of nonlinearity in terms of u, you have linear integral equation. Okay, so until now, we know that this integral equation is a Volta integral differential equations and it is non-homogeneous. Yeah? Okay.
Okay, doctor, clear.
Okay. And the last example of this part here, can you tell me if it is linear or non-linear?
Non-linear.
Non-linear, exactly, because you have
Sine of u.
sine of u of t, okay? Sine of u of t, and you know that sine of u is a non-linear function in terms of u. So you have non-linear part, and it makes this integral equation non-linear. And once again, it's non-homogeneous because function f is non-zero. This is second kind because we have the unknown function u outside the integral, and also it includes Volta part and also Fredholm part. So this is a nonlinear Volta Fredholm integral equation of the second kind. And please solve exercise part 1.2 of the book. If you paid attention to the web page, you could see the main reference. Did you see it? Okay. I uploaded a file, the main reference of your course, as main reference in the web page. You can download it and check the exercises as I remark in the different parts of the lectures. Okay, please solve the exercises. Okay, let's go to the discussion of solution of an integral equation. You know that for differential equations, for example, when you say y prime is equal to y with initial condition, for example, y of 0 equals 1. When you are talking about the solution of a differential equation, you are actually searching for a function y such that when you substitute this y into this equation, this equality will be satisfied. For example, for this special case, if I put y of x equals e to the power x or exponential of x, you know that when you take derivative of this function, you will have e to the power x. So it satisfies, this function actually satisfies in these differential equations. Isn't it? If I substitute this function into this differential equation, I will have this equality sign because the derivative of e to the power x is e to the power x. And also you know that when you substitute 0 in it, you will have e to the power 0, which gives 1. E to the power 0, which is 1. So when I say that the function e to the power x is a solution of this differential equation, I mean that when I substitute this actually function into in both sides of this differential equation, this equality sign will be satisfied. The similar thing is true for integral equation, and when we say that a function is a solution of an integral equation, it means that when you substitute that function into the integral equation, the equality sign will be satisfied. For example, here we want to show that the function e to the power x is a solution of this integral equation. You can see that this is a second kind of ultra integral equation. Let's check that if it is its solution or not. The right hand side of this equation is, by considering e to the power x instead of u of x, we have 1 plus the integral of, instead of u of t, I put e to the power t. So we have the integral of e to the power t dt from 0 to x. By taking the integral from this actually integral, we know that the integral of the function e to the power t is e to the power t. So I have 1 plus e to the power t, t from 0 to x. When I substitute this lower and upper bound, I obtain 1. This one remains unchanged. 1 plus, here I have e
to x
to the power x,
minus 1.
exactly, minus e to the power 0, which is 1. And these two 1 with negative signs will be deleted, so we have e to the power x. So in the right side we have e to the power x, and we know that in the left side we also have e to the power x. So it was easily checked that this function is a solution of this integral equation. Another example, for example here, we want to check that the function x is a solution of this integral equation. So I have to obtain the right hand side and check if it is equal to x or not. We substitute the function u of x equals x in the right hand side. So we have 5 over 6 times x minus 1 over 9 plus 1 over 3 times the integral of x plus t. Here, instead of u of t, we should replace t. dt from 0 to 1. this part remains unchanged, so I write it down, and here I take integral from the second part. We actually have x times t plus t times t, which gives t squared. And when I take integral with respect to the variable t, we will have x t squared over 2 plus t cube over 3. So we have this function from 0 to 1, and we have to replace this lower and upper bound. If you replace these bonds and simplify this part, you obtain x, and you can easily check that the left side and the right hand side are equal. Is it clear?
Yes, clear, Doctor.
Okay, Doctor, clear.
Okay, next example. In this integral, check it please, integral differential equation, and actually this integral differential equation is of Fredholm type because the lower bound and upper bounds are fixed or constants. We want to show that the function x is a solution of this integral differential equation. Actually, you know that the derivative of the function x equals 1. Yeah, u prime of x equals 1. So we have the left side equals 1, and we have to show that the right side is also equal to 1 by considering u of t equal t. We have the integral of t squared dt, which gives the expression t cube over 3 0 to 1, and by substituting these bonds, we will have 1 over just the integral part will be 1 over 3 minus 0, and 1 over 3 plus 2 over 3 gives 1. And we can see that the left side and right side are equal. So this function is a solution of this integral differential equation. Okay. And the next example, you have also an integral differential equation because of the presence of the second order derivative of the unknown function. And also this is a Fredholm integral differential equation. And we have also two initial conditions. First of all, we have to take the first order and second order derivatives of the function u, and you know that the first order derivative of u, what is the first order derivative of this function?
One plus e to x.
1 plus e to the power x, exactly. And what is the second order derivative?
E to x.
E to the power x. Okay. Let's check the initial conditions. You have u prime of 0 equals to 2. If here you put actually x equals 0, you have u prime of 0 equals 1 plus e to the power 0, which gives 1. 1 plus 1 equals 2. So this condition is satisfied, and u of 0 equals 1. u of 0 equals 0 plus e to the power 0, which gives 1. So this initial condition is also satisfied. Let's check the right hand side of this equation with this u of x. Here we substitute the function t plus e to the power t instead of u of t and compute the integral and simplify the result. Then we have in the right side e to the power x. And as we know, the second order derivative of the function u is also e to the power x. So the left side and right side of this equation are equal, and we can say that this function is a solution of this integral differential equation. The next example, we have a Volterra integral equation, and the example suggests that the function e to the power negative x squared is a solution of this integral equation. Then we are supposed to find the constant alpha. So we have to find alpha such that this function is a solution of this Volterra integral equation. For solving this example, we have to substitute the solution in the both sides of the equation. So in the left side, we have e to the power negative x squared, and in the right side, if we substitute, instead of u of t, we substitute e to the power negative t squared, you will have the function t times e to the power negative t squared, and you know that its antiderivative equals e to the powers negative t squared with a positive sign, and if we take derivative of this function, we will have the expression t times e to the power negative t squared. And when we consider the lower bound 0 and the upper bound x, we will have 1 minus alpha over 2 plus alpha over 2 times e to the power negative x squared. If we solve this equation for finding alpha, we find alpha equals 2. So by alpha equals 2, this u will be solution of this integral equation. Is it clear?
Okay, دكتورة clear.
Okay.
اوكي دكتور.
Okay, دكتورة clear.
Okay. And the next example. In the next example, we want to check that if this function is a solution of this first form integral equation, what the value of alpha is. So we have to find the value of alpha by considering this function as a solution of this integral equation. So once again, similar to the previous example, we substitute the suggested solution in both sides of this integral equation and compute the integral part and simplify the result. And finally, let me bring the it seems that I misplaced a section or a part or replaced. Let me check. Yeah, it seems that I forget to bring one page from the book to the slide. Unfortunately, I don't have mouse also. I can't type clearly to find it ourselves. Let me try to write it because I misplaced the next page in the actually next slide, or let me upload the file of book related to this part. It may take a little time because for uploading files, usually it takes time. So please wait for some seconds.
As you like, Doctor, as you like.
Okay, I'm trying to find the file in the meanwhile. Let me check it.
Take your time.
Oh, this is not the file. In the meanwhile, if you have any question, you can ask. I'm trying to find the file with a low size because the site doesn't let me to upload big files, big size files. I'm trying to find a suitable file to upload. If you have any question in the meanwhile, you can ask.
Thank you, Doctor. No have question.
Thank you, Doctor. Thank you. I have a question.
Thank you, Doctor.
Okay, can you see the slides?
Yes, doctor, yes. We see.
Okay, let's continue. You can't see or you see? You can't see? Okay, because of the quality of internet, I think. Sometimes I don't have even the picture. I just have the empty page. But now for me, it's okay. Okay, let's continue. Okay, let's continue. We have started to actually consider example 6, and we claimed that we wanted to find with which alpha this u will be a solution of this integral equation. And for taking and solving this example, we need to substitute function, the suggested function x squared plus x cubed in the left and right side of the integral equation, and actually finally obtain an equation in terms of alpha and solve the equation for finding the value of alpha. So we do the process and substitute.
Excuse me, doctor.
What? Ask.
Doctor, no ever on screen.
You don't have a screen? I think your internet has problem. You don't have the page?
Okay, doctor. Okay, now ever. Okay.
Yeah, I think the quality of internet makes sometimes it difficult to upload the page. Okay. Let me check. Okay, I was explaining that 3 useful remarks. Okay, I was explaining that we have to substitute the value of the actually expression of the solution u in the right and left side of the equation, and finally obtain an equation in terms of the unknown value alpha. And by solving this equation, you know that when you have polynomials in both sides of an equation, you have to set the coefficient of different powers of the x, of the variable x, equal. So when you have in the left side x squared with coefficient 1, you have to have the same expression in the right side. For example, you can see that the coefficient of x squared in the right side, here we have -1, and here we have alpha times 2/5. So let me write it here. So alpha times 2/5 negative here -1 must be equal to 1, because these two expressions are the coefficients of x squared in both sides. So we have alpha times 2 over 5 equals 2. Which by solving it, we can easily obtain alpha equals 5. So with alpha equals 5, we have the claimed function, the function x squared plus x cubed, as the solution of that integral equation. Okay. For summarizing the discussion, 3 useful remarks can be made with respect to the concept of the solution of an integral equation or an integral differential equation. First of all, the question of existence of solution. For example, first of all, you have to check that if an integral or integral differential equation has a solution or not. The existence of the solution should be checked. Solution is unique or not, or for example, there are more than one solution for that integral or integral differential equation. And this matter, usually for considering these matters, we discuss in differential equations and integral equations in more details in the next chapters. And the next topic that is very important for us, we have to consider if a solution exists for an integral equation or an integral differential equation, it's very important to note that this solution may be given in a closed form expressed in terms of elementary functions such as a polynomial, exponential, trigonometric, or hyperbolic function, similar to the solutions given in the previous examples. In all examples we considered, you can easily see that the solutions are in the closed form. You can see an explicit function for expressing the solution. In many cases, in fact, you can't find the solution in such a clear form. For example, you have a form like this, 1 plus x cubed minus x to the power 6 over sorry, something came up and I had to disconnect. Okay, I was explaining that in some cases you, for example, can have solution in such forms. This is just an example. It can be in any form. Plus and other terms. You can't find any function with this series form, or actually you can't find any closed form for this series. So in these cases, the solution of integral or integral differential equation isn't given by actually a closed form or explicit form. In such cases, you need numerical methods for finding an approximation for the solution of these equations. So it's important to illustrate the difference between the two expressible forms, the exact solution in a closed form and the approximate solution in a series form. Here, by an example, we will show the matter. You can see that in this case, when you have this Volterra integral equation of the second kind, the solution of this equation, in next chapter actually, we will see that the solution of this integral equation is such function. This function is the solution of this integral equation. And you can't find any closed form for this series. You don't know any function with this series form. So, to present the solution of this integral equation, you have to consider finite number of terms in this infinite series, and it causes that you will have an approximation of the solution, not the exact solution. In the next case, we consider the nonlinear Ferratold integral equation. This is nonlinear integral equation, and you can check that there are two solutions, u of x equals x and u of x equals 5 times x. Both of them satisfy in this equation. If you replace instead of u of x, x, and also if you replace in all sections that you have u 5 times x, both of these solutions satisfy in this equation. So in this case, the solution of this integral equation is not unique. So being unique for the solution is very important for us, or having a unique solution is very important for us. And in the next chapters also, we will consider the situations or conditions that are necessary to have a unique solution. Here you can check it easily. You can replace u of x, x, and also u of x 5 times x, and check that both of them are solutions of this integral equation. And the reason is that here you have the nonlinear term in terms of the unknown function u. So this integral equation is a nonlinear integral equation. And in many cases of nonlinear equations, we have more than one question. So the uniqueness concept is not applicable for this example and also for many other nonlinear problems. And these kind of problems, actually nonlinear integral or integral differential equations, will be discussed in a chapter separately, and we will discuss about their solutions, how to find their solutions, or how to introduce methods for finding their solutions in a special chapter. Okay, you saw that there were different situations for integral equations and also integral differential equations. And if I want to summarize today's discussion, we saw, first of all, we have been familiar with the concept of singular integral equation. Then we talked about integral differential equation of Fredholm and Volterra type, and also the mixture of Fredholm and Volterra integral differential equation or integral equation. Also, we checked how, actually we didn't introduce any method for finding the solution. We just checked that some solutions or some functions are solutions of some special examples, and we checked that if a function is given to us, we can check if it is a solution of that integral equation or not. We finally finished our discussion by saying that there are many nonlinear equations or integral equations that the solution of those equations are not unique, and there are more than one solution for them. So it's very important to consider examples or equations that we know that the solution of these problems is unique, and there is no more than one solution for them, because when you want to introduce methods for finding the solution, it's important to know that what are you trying to, or what you want to find as a solution of that equation. I think for today, solve also the exercises of section 1.3. So for today, you exercises part 1, 2, and 1, 3. You can see that in part 1.2, you have to recognize the actually properties of integral equation, to recognize that if the integral equation is Fredholm type or Volterra type, second kind or first kind, homogeneous or non-homogeneous. And in the exercises part 1.3, you have to check that if a given function is a solution of the integral equation or not. If there is any question, you can ask.
Thank you, Doctor. No have a question.
Thank you, Doctor. I now have
You're
a question.
Thanks, Doctor.
Okay.
Thanks.
As you see, the discussion is easy. The topic is easy. So please study well. Be familiar with different kinds of equations. And then be ready to have the next lecture on Saturday. Okay?
Okay, Doctor.
Inshallah, Doctor.
Inshallah.
Inshallah. Okay, so it seems that there is no question. So goodbye, everyone. Have a good day.
Goodbye.
Goodbye, Doctor. Have a nice day.
Thank you.
Thanks.